All right, welcome. Thank you. Maybe there's a 102 student or two online that doesn't know me, so you'll have to hear this again. So, I was in the program, graduated in this 2-year curriculum in about, I don't remember, 3 years ago, probably. And I got into the program coming off of being laid off, or not laid off, having my work career ended as an engineer out at Pulp Paper Mill in 2010, and we got assistants, so I thought, hey, let's do this energy tech program. I get medical and stuff, and really enjoyed it. And I worked out at the Frenchtown Pulp Paper Mill for a long time, 37 years. Started as a environmental guy and engineer, and chemical engineer out of Montana State. Started 1973 at the mill, and worked my way up in various positions and had a lot to do with energy out there, and we all did. A really fascinating process. And also, when I was at school, I did some substitute teaching. I was at the Missoula College. I did substitute teaching in high school, math, science, and other stuff, and enjoyed it. And had the opportunity to lecture for Brad a few times a few years back, and was lucky enough to become adjunct faculty here and taught 101 and 102 for a couple semesters anyway. Now with things going on, Brad's doing it, so he's gone, and Tim's, I think, sick today, so you got me. So today, for certain, this is yours. One of the values of Common is you get to influence what we do if you want to. Okay, so if I get in somewhere you don't want to go, or if I'm missing something you really want to know about, let me know. And if you got any specific questions, I'll do my best to answer them. I do have a sample problem, and I will get into lecture from the text when we get there. We didn't do much of that last class, and there may not be much this class. So any questions off the get-go here you got that I can entertain? And again, if they pop in your head as we're going through this, interrupt me. Somebody help me with keeping time. By about 3:45, I should, by 4:45, I should maybe stop the recording and count that as one segment. If I started it. Yep. So, what did I do with that thing? Don't see it. Well, you can find it pretty quick. Okay. Can you read that? Yeah. Too little? Here, let me get it bigger. There you go. Just take it down just to, number one. It's a 3-part problem, but actually 3 problems in one. And in the last class, we did the same kind of problem related to coal. We're going to look at wood here. But wood is bioenergy. It's a biofuel. Can be a biofuel. And I'm kind of mixing here a little bit, but it is true. I look at those wood chip cars there out by Bonner. They're producing chips from logs, as we did out the Pulp Paper Mill, although we made paper out of them. And most of these chips, I think, out of Bonner are going to like Wallula, Washington, to a Pulp Paper Mill over there. As they make those chips, they also have bark that's coming off those logs, and finer material, sawdust and knots and whatnot that's not suitable for paper making. Well, suitable for burning. May not be the best stuff. So I'm going to look at what a rail car of this wood would generate as electricity in a wood-fired boiler. Okay? And we at the facility had 2 of those wood-fired boilers. One old one we shut down in later years, one newer one, that generated about 400,000 pounds per hour of 600-pound steam that was used throughout the process for paper drying, evaporation, turbine generation to make electricity. We produced about 1/3 of electricity we needed out that facility by burning that material and burning recovered black liquor, which is part of the recycle process. Anyway, so I thought, well, geez, that chip car, what can it produce for electricity? What can a car of coal produce? Well, we calculated that last class, and you guys are very advanced 102 students, so you know this coal thing inside. Now let's look at wood, where to buy energy. So, as you may remember, and as Levi saw the previous class, when you go to solve these problems, I'm big on listing, read the problem, okay? You might go through and underline what you're supposed to find, double underline what you're given or vice versa, and write it down, and always write your units down. It'll help you a lot towards solving that problem. So I give you some parameters here. A typical rail car of hog fuel holds, these numbers are very approximate. It could be anywhere from lighter than this to heavier, but 80,000 pounds of wood. Okay, that doesn't include the car weight, that's net off of that. That's how much wood's in there. We know the typical heating value of air dry wood very generally is 15 gigajoules per metric ton. And a typical wood-fired boiler wood energy to electrical energy efficiently is approximately 30%. It's very, very general numbers. I would say most of the wood we received at the mill, because of its moisture content and the kind of wood it is, and most of the wood around here would be less than 50 gigajoules per ton. And we'll look at a table here in the text when we get far enough that shows air-dried wood at 80% dryness as 15 gigajoules per ton. We never got wood that dry. And they show wood at about 60% dryness, if I remember right, or 40, that's about 6 gigajoules per ton. A big difference. But let's use 15 for what we're doing here. The first problem, we want to calculate the amount of electricity this hog fuel could produce. And I warn you, let's be careful of the units. I'm giving you the weight of the car in pounds, and we're knowing the heating value of the wood as gigajoules per metric ton. Well, those are two different units. We've got US units and metric units, but that's very typical of what we run across solving these problems. And very typical of what you'll run across as you get into your readings and see an energy system out there and start to go, well, what is that really worth? You know, you might be reading it and it's in metric, or you might be reading it and it's US and you know how to solve it in metric. And it took me a long time when I took the class, because I dealt in US units out the mill. You know, we looked at numbers constantly because it was big bucks. And these texts are wonderful, but this metric, and the solutions to most of the problems are metric, so that's what we're going to use. So what I would do is calculate maybe how much weight's in that hog fuel car as metric tons. From that you can calculate how much energy as joules, megajoules, gigajoules, whatever that is, and convert that to how much electricity that is at 30% efficiency. All right? Once you've done that, we're going to compare. And when you get to that first part and you get it done, let's go in there and look at how far you've come and what you're doing. We're going to compare that electricity to the electricity that is made from a typical solar PV array. And I've picked the Lifelong Learning Center up the street here at the university because I was involved in auditing its performance, not as just as a part of looking at all the green energy projects that have been completed at U of M. And over a two and a half year time, that those 10 solar PV panels produced an average of 2730 kilowatt hours of electricity annually. All right. So we want to know how much electricity per day that is, and I want to know that hog fuel car the electricity it can produce, how's that compared to the daily production from those panels? Okay, so one rail car of hog fuel is equivalent to how many days of production from that facility, or how many facilities per day would it be? Okay, either way. And the same kind of thing, the second problem, I'm throwing capacity factor at you, and I know you guys know about capacity factor. Capacity factor, again, is the amount of electricity that is made from a system, or energy made from a system, divided by the full rated capacity running full time. All right. So in this case, you got a 1.5 megawatt turbine. What's megawatt? Is that power or energy? Power. Hey, man, these are second year students. I like it. So that's a rate. That's a rate. That's at full capacity what that turbine can make. All right. If that turbine ran at full capacity for a full day, it would make 1.5 times 24 hours of electricity. What's electricity? Or energy? Yeah. I'm looking for a different word, but you're correct. It's quantity. It has joules or watt hours or whatever it might be. Okay, so that's the problem. All right. You want to give a few minutes on it, and I'll shut up. Okay. And the appendix in the back are always really good to use for these, I think. Gotta make some notes. Big book out. Pause this. All right, we're back with you again, and the students were working on this problem. I've summarized problem 1 here with our given and find. So we want to find out how much electricity this hog fuel could make as kilowatt hours. Okay, and I interchangeably use wood, hog fuel, and chips for this exercise. It's all the same. We got some wood here. It's in a rail car. We're going to make electricity out of it by burning it in a boiler, make steam, drive a generator. And that boiler is about 30% efficient, we're going to assume. So of the energy going to the boiler, 30% of it ends up with electricity we could use. And the heating value, or the energy value in that, the energy density in that material, that hog fuel, is 15 gigajoules per ton. That's certainly overstating it, but there are woods that do have that. Okay, and we're just doing this for a comparison. So where do we go? Anybody calculate to completion, or calculate the weight in tons, or the value of energy as either gigajoules or megajoules in that hog fuel car? Yeah? What'd you get?
I got 163
gigajoules. I did it a little differently than that. No. That isn't what I got. I got 500 and...
oh, yeah, that's after the 30%.
Oh, okay. So, yeah, you're right on. You're right on. Well, how'd you get there? Because I might do it a different way, and these people might want to do it your way. If I can write it, if I can find my pen again, I'll write it down. Let's try this. There it is. Okay. So would you start with the weight of the car, 80,000 pounds?
No, I just started with 15 gigajoules per ton.
Okay, that's another way. Gosh. Let me... God. Sorry. Frustration abounds here. Maybe that was it. say 15 gigajoules per ton, right?
Yep.
And then,
And then times 1 ton over 1,000 kilograms to convert to tons.
right, that's in your appendix if you don't remember that offhand. 1,000 kilograms per metric ton, yeah,
And then times 1,000 grams, or 1 kilogram over 1,000 grams.
okay. Okay,
Times 453.6 grams per pound.
nice. Okay, and I rounded it off, okay, okay,
Times 80,000 pounds.
okay.
And then you can multiply that by 30 over 100%.
I'll use .3, you got it, okay, whoops, maybe not.
You did the answer, gigajoules.
So that is, I didn't do it that way.
163 gigajoules.
163 gigajoules, okay. And that is per, okay, per car, right? Okay. And I didn't, here you go, I broke the rule, Shauna, for a car. Okay? Yeah. Then where'd you go?
So for the second part, first I think it has to get kilowatt hours per year and kilowatt hours per day. So,
Okay,
I just did 2,730 kilowatt per year times 1 year over 365 days. Convert that.
okay. So you went, that's, I call that the second problem.
Yeah.
Okay.
Was there any more on the first problem? Maybe I missed it.
Well, yeah, it asked, what did we ask to find? Kilowatt hours of, in kilowatt hours of electricity from the hog fuel, yeah.
Okay, yeah.
You did
That's
that
part of the
subsequently? Okay.
Yeah.
Go there first before you get into the Todd production, and maybe that's where you were. Okay,
So basically what I always do, rather than mess with the hours for gigajoules,
Yeah.
is just do like 163 gigajoules per car
okay,
times, what is it, through 1 gigajoule hour is 3,600 gigajoules.
okay. 3,600 gigajoules, okay,
Over 1 gigajoule hour. And then
okay,
to get that to kilowatt hours, you just do 10 to the 6th kilowatt hours in 1 gigajoule hour.
yeah,
Or gigawatt hour.
so you got gigajoules out, gigawatt hour?
Yeah, those are gigawatt hours. Sorry,
Okay,
I'm getting
yeah.
mixed up.
So, and there's a factor in the book that does it a little differently, and I use that 3.6.
Mhm.
What is that factor again? Let's write that up here. I find myself. Here we are. Where'd it go? And you did that out longhand, but it's 3.6 megajoules per kilowatt hour.
Mhm.
All right. No, I can't write it. Megajoules. Okay, and you did it this way, but there's a conversion in the book that's exactly that, but it's in different terms.
It just moves
Yeah.
to 3 powers.
Yeah. Okay, you all got that? Okay. So where'd you get out of that then? Or we got more of that calculation?
I kind of did it all in one stream, so I never.
Well, no, go ahead. Continue your string. That's fine too. Some people don't like to do it that way. Some do.
So that'll get you to kilowatt hours per car.
Okay. I got you.
And then from there. Let's see how we go.
That's the amount of kilowatt hours per car in the cold, not applying efficiency. Right? Is You gotta apply the efficiency, or you already do that?
Yeah.
Oh, you already did it, okay,
163,
yeah, good,
yeah.
good, okay.
Yeah, I gotta think for a second how to go from here, because I did it kind of in a different order.
Okay,
Let's see, what we got? We got kilowatt hours per car.
that's all we need. That's where we wanna go.
Oh, yeah, okay, the next part's problems.
Yeah, so I see what you did. And we end up with 45,000 approximately kilowatt hours per car. Is that what you ended up with? That's look right. Yeah. Yeah. Looks right. Million divided by 3.6 is, 163 divided by 3 is around 4 something.
Yeah, 45,277.
Yeah, so it's around 45,000 kilowatt hours per car. So that is, what's that telling us then?
That's a lot.
Yeah, those chips can make 40, you know that coal, the same size car of coal or close to it, can make about over 200,000 kilowatt hours of electricity. Wow.
Crazy.
Well, that exhibits, that's a visual of the issue we're facing getting rid of coal. Its energy density is so high, it can make so much energy for us, it's the easiest thing to use. It's the most economical. What were they doing way back when, you know? It's also the dirtiest, but, okay, but bio's not bad then. This wood's not bad, 45,000 per car. Now let's go to problem 2, right, as I call it. Yeah. And that's where we're taking the Todd solar system, right? Solar PV array. Did I get to the end already? Goodness. Array, okay. At, what did we say? 2730 kilowatt hours is what it can do per year. 365 days a year. So in a day, that system can make 7.48 kilowatt hours per day. Oh, when it does that, I do a goofy line. Per day. And there's other ways of doing this, but for speed here. And I didn't ask the question very well in this thing. What I'm talking about is, there's two different ways of stating it. That solar system average is making this 2,700 kilowatt hours in a day, okay. This rail car of chips, how many solar systems producing electricity for that day would be required to equate to that? So you simply divide the two. It's a lot. Coal, it's enormous. So you got 45,000 approximately kilowatt hours per day of coal. Because we're talking about one day for this car. A panel, the system, a typical system is about the same size, a residential system, per day. That's a lot of panels. It's about 6,000 panels, or 6,000 systems. Follow me? It's a crazy way to look at it, but I wanted to find a way to compare it. Okay. Another way would have been to look at coal strip, for example. How much electricity is it making out of coal per ton of coal? Okay. Or per day, and then it's just too enormous, it's so big, you know. Okay, but 6,000 of those systems. For coal, it's 5 times that. It's about 30,000 of those systems, 25,000. Yeah.
That 45,000 kilowatts hour per day, is that coal?
Yeah, that's coal. That's what coal. That's coal. I meant, yeah, no wonder you're all looking at me funny. I'm mixing and matching. I'm thinking about coal so much. Yeah, you're right. It's chips.
Okay, I was like getting confused there.
No, and you should have been getting confused, yeah, what I was saying, writing. Let me get that right now. So that means that one chip car, to equate to that chip car in a day, we'd have to have 6,000 systems. And that Todd system is not a huge system, though. It's 10 panels. I mean, you see a lot of systems around town that are 10 panels. Could we have 30 or 6,000 systems around town? Yeah. But my God, that's only equates to one chip car in a day. That's not one chip car for one in a day. Well, my God, we were moving wood at hundreds of chip trucks and dozens of chip cars in a day out the pulp mill. So it gives you an idea. And you don't even want to talk about coal. I mean, hundreds of coal cars are required a day to fuel Colstrip. My God. Okay. Let me try to correct that sucker. Get this thing up here, Mark. Where'd you go, dude? Here. There it is. Thank you, Sean. That is really confusing people. Mix and match. All right. But that sun's around as long as I'm going to be around. And those panels have a life of 40, 50, 60 years with almost no maintenance. There's no batteries involved. If you got a system with batteries, you got some maintenance. No batteries. It's net metering. Goes right into the supply of that electricity for that building. And when it's, let's say it's a weekend and nobody's using electricity, with a net metering agreement with the Northwest Energy, electricity goes back to the grid and you get credit for it later when you're using it. So it's a win-win. However, you need lots of it. Okay, let's look at a wind turbine then. Problem 3. Anybody get that one all the way done? So, the wind turbine. The capacity factor thing throw you, because I hadn't really gone over that. There it is. Okay. So capacity factor is the achieved, am I spelling that right? Electricity divided by the electricity produced at rating, okay, running full time. I say it differently all the time. I put my finger over there. Okay. So Shauna was correct that one turbine of the 90 plus at the, or 90 at Judith Gap at full capacity can make 1.5 megawatt. Okay. If it ran for 24 hours in a day, because we're talking about wanting to know electricity per day here. Or did I wrote that out? I didn't. Okay, that's what it makes at full capacity, but over time we average about 30% of that at that wind farm. Okay, so we're making in a day on average 10,800 kilowatt hours per day. Okay, and I got 1,000 to apply here too that I didn't do. Yeah, there's 1,000 kilowatts per megawatt. You got me there. You know, better write that down correctly for the people that aren't here. So let's go here again. Get the big hurry. Maybe you can do it there. Okay? And that's so again, it's the coal, or the chips, there we go again. Chips can do 45,000 approximately. One chip car in a day. And these turbines can do, one turbine 10,800. We got about 4.5, a little less, turbines. So the wind's turbine, of course, you get a lot of money in one wind turbine. 300 feet tall, 300 foot in diameter, lots of gears and oils, cooling systems and whatnot. Quite a bit of maintenance required. Control systems to what's the right term? Put it into the grid, make it right with the grid and with the other turbines and all that, but still, 4.5 turbines. But that's one chip car in a day, and one turbine's average production in a day. Again, that shows that we've got a lot of resource out there possible from wood as a bioenergy source. There's tons of problems with it. I think Tim touched on some of that. Moisture. We're assuming very low moisture wood here. That's not really the case. If you're going to go out and start up your boiler down the street, the UM boiler, it would have had wood more like 50-60% dry rather than 80, maybe 40% dry. And again, coal, you can be 5 times that amount. You can be more like 20 turbines, 25. Okay, so gives you an idea of what we're facing relative to getting rid of coal. We've got some great technologies, quite robust, but there's issues. It's going to take a lot of solar systems, and that's probably not the answer against a power production plant. No, it's very useful neighborhood kind of solution. As it gets cheaper and cheaper for us to do and save our own money. The wind is problematic. You got to put it where you got wind. A lot of times that wind isn't close to transmission. You got to build big 240 kilovolt transmission lines. A lot of money. But with subsidy, wind is closest to being economical against coal as anything. Thus, you see the great growth in wind in Montana really going on. Building a new one over in Billings. Built new ones up at Glacier, three of them in the last 5 years. A lot going on. Okay, let me get out of here. Any questions on that problem solution? It's more about the system than anything else, and the idea that with our resources here, we're learning in 101 and 102, we come across something, we can evaluate it in our minds a little bit. Get a visual to it. That coal car, my gosh, what can it do? Okay. You come across something in your readings online, this system, this new idea can do this or that. Well, how much impact might that be? And now you got some quantities in mind. Now we haven't talked about usage, that's a different thing. But we've got resources in our book to figure that out too. Very generic kinds of, with our very high usage in the United States. Okay, let me stop this and take a pause. Here it is.